Well, today's the day, guys. We're up to the pointy end of the R35 project here. So Davo's been busy with all of the wiring. I've gone through and configured the ECU, so we've seen the thing start, we've seen it run, but today, it's D-Day. It's time to get it on the dyno. So the goal today is to get this car on the dyno and start making some power. Keep in mind, this is a factory VR38 engine. So I'm expecting sort of about 350 kilowatts of the wheels, a very conservative power level, but there's good reason for that. This is a brand new car that's got so much fab work, there's so much in it that we want to take it out to the circuit. We want to shake it down and make sure everything's right before we start to wind the power up. Right, so we've got plenty of work to do. Davo, are you ready? Now comes the fun bit. Let's get it on the dyno. The first thing that I normally do once I get a car on the dyno is relax. And I know that sounds weird, but the first thing that we need to do is to just calmly go through the ECU setup, go through our sensor configuration so that we know that all of our sensor calibrations are done correctly, all our sensors are reading correctly. That way, when we get to the tuning part, I know that I can rely on all of the sensor information that's coming into the ECU. So now I'm just going to go through our full sensor list and make sure that all of our calibrations are entered correctly. I've set up a screen in my software here so that I can see all of the sensor channels coming into the ECU. I'm going to make sure they're reading right. Then we'll move on to the next bit. The first one, manifold pressure. It's one of the most important sensors. It's measuring the pressure in the intake manifold, and that's one of the things that's used in the fuel model a huge amount. It's the sensor that we measure all of our ignition, or we map all of our ignition and all of our fueling against. If I go into my calibration here, 0 to 60 pounds, I know that this has got a 5-bar map sensor in it, measures up to 60 pounds of boost pressure. The next sensor down, oil pressure, a really, really important sensor to have the right calibration for. If you've got a 0 to 150 PSI oil pressure sensor, which is probably the most common one, if you put the calibration in as a 0 to 250 pound sensor, you're going to end up displaying a different oil pressure and you're going to end up confusing yourself, and that's going to be a problem when we go to set up the engine protection later, as well as trying to chase oil pressure that you do or don't have. Coolant pressure, I'll come down to the next one. This is one of the first cars that I've set up in this way that I think is a really great idea. So this car, instead of relying on the factory coolant temp sensor and then adding another hole to set up our coolant pressure sensor as well, because we want to see the pressure in the cooling system on this car. Once the thing's all fully set up, it's going to be highly strung. If it does push a head gasket or has some kind of engine failure, one of the first ways to mechanically see that is in our cooling system. When the cooling system pressurizes, we know that we might have an engine problem. In this car, I've set up one of the Bosch pressure temp sensors, so it's measuring the coolant temperature as well as measuring the cooling system pressure out of one sensor, which is one hole in the cooling system. Mechanically easy to fit, easier to wire, and just all in nice one tidy package. So I know that the calibration for that sensor is 0.5 to 4.5 volts, 0 to 150 PSI. I could also click on the little button here, load from file. If I cruise down through this huge list of all of the available sensors, we'll get down to pressure. In there somewhere, there we go, Bosch pressure temp sensor. If we click on that, that brings the calibration in as well, so a nice easy way to do it. Fuel pressure sensor, another really important sensor, so we need to make sure that we set our base fuel pressure correctly before we start doing any kind of tuning. So all I'm going to do here, I'll just turn our fuel pump on, turn our pump off. We've got 50 pounds of base fuel pressure. So that's with the fuel pump running, it's going through the fuel pressure regulator, regulating at 50 PSI, and then returning to the fuel tank. I could go through this list, but you get the idea of what's happening here. So I'm just going through and verifying that I've got the right calibration for each sensor and that each sensor is displaying correctly. So now I know all my sensors are reading correctly. What do I do with all that data? There's so much on the screen and there's so much happening while I'm on the dyno that I like to make the most of my engine management system, and I want it to be helping me as much as possible, because if something happens on the dyno and I'm busy looking at something else or I've missed something, I want the engine management system to pick it up while I'm on the dyno. And that's why I turn the engine protection on as soon as I get in the car, before the thing's even started and running. Why do I do this? Well, while I'm on the dyno, if I've got all the fans and everything happening, I'm checking the power level, I'm adjusting the mixtures, I'm looking at the wideband oxygen sensors, I'm double checking the oil pressure. It's very easy to just overlook the coolant temperature, which might just be rocketing, cruising away slowly. Before you know it, you're at 120, or 100 degrees Celsius, you're at 220 Fahrenheit, and you look down and think, oh, something's happened. Something silly might have happened, but there's just so many things to be looking at. So turn the engine protection on before you start tuning the car. One of the other really nice things about doing that is that if you set sort of a bunch of generic values and a bunch of generic limits for all of your channels, when you're on the dyno running the car, you might hit some of those limits. Whereas and you can adjust those values. Whereas if you fully tune the car, then turn the engine protection on, then send it out, you don't really know if you're actually hitting any of those values in everyday driving. So it's best to set the engine protection up first, encounter any of those problems while it's on the dyno, then as soon as it comes off, you know that it should never ever hit any of those engine protection limits. The first engine protection function that I always set up is the engine oil pressure. Without oil pressure, the thing's gonna be a disaster. So that's always the first one that I set up, and I set it up really aggressively so that if the thing doesn't have as much oil pressure as I want, it's going to turn the engine off. But keep in mind, different styles of racing and different people want different results from the engine protection. Personally, I think that if the engine has no oil pressure, it's going to stop sooner or later, so I'd rather stop it sooner. Whereas if you're setting the thing up for like a boat racing event, for example, some of the boat racing guys, they want to drive the engine until they feel something fail so they can slow the engine down on their own accord, because it's pretty dangerous to try and slow a ski boat down from 120 mile an hour to 0 instantly. So you might always want to check with the driver of the boat or the driver of the vehicle to decide on how the engine protection should be set up. But for me, in this car, if it's got no oil pressure, we're going to shut it down. So if I cruise down here, oil pressure, diagnostics, I'll set up our operating minimum so that if the engine's above 500 RPM, it needs to meet this condition for longer than 0.75 or 3/4 of a second. It needs to be over this amount of throttle position, which I set at 0%, meaning that it's always looking at it. And the diagnostic trouble code severity level, level 3, which I'm going to set up as the most aggressive level. If we come up to here, our oil pressure minimum that we map out versus engine RPM. So as a rule of thumb, I would normally do at 1,000 RPM, I want 5 pounds of oil pressure as an absolute bare minimum. At 2,000 RPM, I want 10 pounds of oil pressure. 3,000, 15 pounds, 4,000, 20 pounds, 6,000, 30 pounds, and 8,000, 40 pounds of oil pressure. I sort of find that across all the styles of engines, this is about the bare minimum oil pressure that you really need. You can talk to your engine builder, they might have better ideas on what the bare minimums would be and what to expect. Always trust what the engine builder tells you, and then that way you can set this up so that if it goes below this, we're going to shut the engine down. Next, I'm going to go to my engine protection function here. Sorry about this, I'm just having trouble sort of creeping over to look at this, and I've got my microphone here. Everything's sort of a bit crunched up in this car because we've got no windows in it at the moment. I've got to put the little sock over the microphone here, otherwise we're not going to hear anything later on when all the wind starts coming in from the dyno fans. If I click down here across engine protection, you can see here that we've got our 3 different severity levels and what happens when those severity levels are met. So when I do a car setup, I normally talk about engine severity level 1 as something that is not really critical, but you should know about it. Say for example, if the coolant temperature goes a little bit high, if the inlet air temperature gets a bit too high, maybe the battery voltage goes a little bit too high or too low, I want it to throw a trouble code. I want an engine check light to come up on the IC7 dash. And I want a rev limit on the engine at a higher rev limit, let's say 4,000 or 5,000 RPM, so that when that does happen, I know about it. It's not super critical and I'm not going to shut the car down, but I would like you to pull over, have a bit of a look and see what's going on. Engine severity level 2, I set up as something that is a little bit more important that you do need to take note of. I use that for our wideband oxygen sensor engine protection levels mainly, so that if we're over a certain throttle position, over a certain manifold pressure, over a certain engine RPM, and the engine is leaner than, let's say, my values are sort of about 13 to 1, above 13 to 1, and the engine under high load, I like to limit the engine because that's telling me that I wouldn't typically tune an engine there. So we might be running out of fuel, it might have a clogged fuel filter, it could be a range of different things that are happening. So best off to limit the engine and stop it from making power again. So in order to do that, I can come down here. I'm going to do the rev limit end at, say, 3,000 RPM so that you can't go out thrashing the car again. Drive-by-wire max throttle position, 40%. So even if you do try and go to full throttle, the throttle blade itself is only going to open to 40%. So you can't put much load on the engine. You can't do any damage. The last one, active condition. So basically what this is asking is, when do I want this engine protection to happen? During this drive cycle, we call it, meaning that when we start the engine, that's a drive cycle. If I turn the engine off and then turn it back on again, it's going to clear that code. You could try and drive it again. If it meets that condition again, it'll go into the engine protection. If it doesn't meet that condition, if it was just a one-off, you'll be able to drive and everything will still be fine. It's always worth noting that the engine protection stuff is there for the engine's protection. I know how tempting it can be when you're at a sick drift event and your car keeps going into engine protection to just reset the ignition, reset the ignition, reset the ignition, scream at it, yell at it, go online and just do whatever. But if the car's got no oil pressure, it's got no oil pressure, and the ECU is trying to do you a favor by shutting it down. Take note, look through all your sensors, find what the actual problem is that's turned that engine protection on before your engine fails. While we're in the sensor area, one of the really cool things about the NEXUS series ECU that you might want to have a look at is the onboard oscilloscope. So this thing's got 4 channels of onboard oscilloscope that can be triggered from a 5th channel in the ECU. So if you don't know what sort of crank sensor teeth or cam sensor teeth pattern you have on the engine, luckily on this one it's a fairly common and popular engine, so I know exactly how to configure it. But if you didn't and you had a unique number of crank teeth, a unique number of cam teeth, all you would do, open your oscilloscope, configure it to be looking at our trigger voltage, so the voltage coming straight in off the crank sensor, our home voltage, so that's the voltage coming in off the cam sensor. The other one that I've got set up here is engine angle. So being a 4-stroke engine, this thing, the crankshaft spins 2 times to the camshafts 1 time. So we reference that engine angle as 0 to 720 degrees, so 2 crank revolutions. All I'm going to do here, I'll get this thing started and running now. I'll hit trigger to get the oscilloscope up and working, and we'll be able to see all those voltages and we'll see those little teeth coming through in the oscilloscope. So we'll start her up. And there it is. So I'll shut this down now. So I'll shut this down. So from there, we'll get a little screenshot there so we can see the actual teeth coming through. And I'll also put up a picture of the flywheel and the camshaft on the VR38 engine so you can see the relationship between those teeth coming through and how that looks on the flywheel and on the trigger that's on the camshaft on this engine. So that's the onboard oscilloscope. Everyone's been asking that for a really long time. It's there. It's great to have, really good to do any diagnosis work. Now I'm on to the monotonous task of actually tuning the engine, and that is tuning the fuel maps, tuning the ignition map, and tuning the target variable cam control angle. So these 3 tables are kind of the base that need to be set. Then we can set up all of our other tuning parameters and corrections around those. So the first thing that I'll do is just rough in a basic ignition angle map. So when the spark plug fires relative to top dead center. I'll rough in a cam angle map, which is how far advanced the inlet camshaft is. So this has got continuously variable camshaft control. So like a vernier cam gear on the front of the cams, but I'm adjusting them electrically across all the RPM sites and all the load sites, as well as doing the fueling. So how much fuel to put into the thing at every RPM site and every load site. So the way that I like to do this, I'll get the dyno to hold the engine at about 3,000 RPM, give or take. I'll go through using my foot to regulate the load on the engine, and I'll get as much vacuum as I can get. I'll suss out where the fuel map is, and I'll kind of make it so that, massage it so that my volumetric efficiency table looks about right there. I'll bring on full load at about 3,000 RPM, get a bit of an idea of what the fuel map's going to look like there. Then I'll come down and do everything below 3,000 RPM. Then I'll start coming up and up and up, doing what I call steady state tuning, which is holding the engine at a specific engine RPM, then tuning all of the fuel map, or tuning all of the load or the manifold pressure sites I can get to. There is a point where steady state tuning isn't a great idea because the engine is just working so hard and making so much heat there. That's the time where we'll go over to what we call ramp runs or power runs. We'll start doing power runs at very low boost pressures. So whatever the wastegate pressure of the engine is, so let's say 7 pounds or 9 pounds of boost pressure, something like that. That'll give us our base engine power, so the lowest power at the wheels that we can possibly make. Then we'll boost the engine up and up and up until we make as much power as it can possibly make. Then we'll go back through and do our boost by gear stuff so that we can make the most of getting all the different power levels out of each gear so the thing's actually drivable. And just keep in mind, in this particular car, it's a fresh build, fresh everything. So we're not going for a horsepower hero here. We're going to make enough power so that Brian can take the thing to the track, bed the whole car in, go and spanner check it, make sure everything's right before we then wind the power up. So I've spent a couple of hours going through the fuel map, the ignition map, variable cam control map, and the boost control target tables, putting everything together. I've done my steady state tuning stuff. So now it's time for a power run and we'll see what's going on. We just made 280 kilowatts on 10 pounds of boost. It's awesome power for 10 pounds of boost, but remembering the VR38 in a factory Nissan R35 makes about 300 to 330 kilowatts of the wheels, something like that. So we are very, very conservative at the moment, like we said, but now that we've done the 10 pound sort of setup and it's making good power, the mixtures are nice and flat, we've got our ignition time where we want it. Now, it's time to set up the boost controller. So in order to do that, we've got some boost control solenoids that are attached to the internal or external wastegates. In this case, it's got 2 external wastegates. And I'm going to configure the software now to pulse those solenoids in order to bleed air off the bottom of the gate or between the top and the bottom of the gate, depending on how the wastegate's plumbed. In this case, we're bleeding it off the bottom of the wastegate in order to do something to increase the boost pressure from the spring pressure of about 10 pounds up to roughly double. So we'll end up at somewhere around 20 pounds of boost pressure by bleeding air off the bottom or the hot side of the wastegate. I'm going to set up our boost by target gears as well here. So the first thing that I'll need to do is set it up so that the engine management system knows exactly how much air to bleed off those wastegates in order to make the boost that I'm requesting. And to do that, we come down to our boost control tables and we set up our closed loop base duty cycle values. So this is the amount of air that needs to be bled off the wastegates in order to achieve the desired boost pressure. Think of this as our sort of start position. So this gives the engine management system a helping hand to get there. Then it falls into what we call closed loop boost control, meaning that it looks at the pressure sensor in the intake manifold, then it looks at how much we're targeting. So say, for example, we're targeting 15 pounds of boost pressure. The manifold pressure sensor is telling us we've got 13 pounds of boost pressure. The boost control strategy will take over, bleed off a little bit more air off the wastegates in order to get our target of 15 pounds. We also need to go in and set up our closed loop target pressure table. So I know it gets a bit complicated here, but this is what your tuner's for. If you go through the software, you can set all this stuff up. In the bottom left-hand corner of the software, down the bottom here, you can see the descriptions for all of these tables that I'm talking about. You can read through them. There's a really nice help section in the menus as well to be able to describe all these tables because there are a lot to remember. Once we've set up our base duty cycle stuff, I've now set up a table that is gear dependent and throttle position dependent on the engine. So what this does is in first gear, we're always targeting 10 pounds of boost pressure. In second gear, we're targeting somewhere between 11 and 13 pounds of boost pressure, depending on how wide open the throttles are. We do this because mid-corner, if you're circuit racing a car, if you're part throttle, you don't want huge boost pressure at part throttle. You want a small amount of boost pressure there so it's a lot more linear to drive. We also pull boost out of it in the lower gears in order to control the traction a little bit more. This car does have the Bosch ABS system. It does have 4 wheel speed sensors with our differential traction control system, so our wheel slip control strategy. But it's best to map all of this out while we've got the thing on the dyno so that you can control that power nice and easily when you get to the racetrack. As we come up to the top here, in 6th gear, at above 60% throttle, we're going to be targeting 20 pounds of boost pressure. That's about the limit that we're sort of going to push this factory engine to in order to get a bit of longevity out of it as well. So now we'll go through that. We'll do some power runs. We'll configure our boost controller so that doesn't matter what gear we're in, we'll get all of our varying boost levels. It is a little bit more power than I expected it to make for us to go and shake the car down. But when you're on a roll, when it all comes together, when it's all just working, it feels great. So that's a huge amount of power and I'm really, really happy with that. I've also gone through and set up our boost by gear targets. So what I've done, all of these power runs you can see on the screen here are all in 6th gear. I've done that so that we get nice long power runs on the dyno so that I can set up our boost controller appropriately. And you can see here on the screen, I've got 1, 2, 3, 4 different power levels showing. This is all with varied boost pressure. So I've configured it so that we've got 10, 12.5, 15, 17.5, and 20 pounds of boost. And that's kind of resulted in power levels somewhere between about 280 to 430 kilowatts at the wheels, dependent on what gear we're in and at what throttle position we're at. So then when we get to the racetrack, we've got a really good base to start with. So now to the bit of the video that I'm the most excited about, the sequential gearbox control. This thing is awesome. It works so well and I'm so excited to rip it through the gears. So what I've done, I've set up a gear position sensor on the shift shaft inside this gearbox. So what that means is that there's a position sensor in there that tells the engine management system exactly which gear the gearbox is in or is not in, meaning that it might be between 2 gears. And that's important information to know when we're about to do our downshift throttle blipping or ripping it up through the gears and doing our ignition and our fuel cuts and our ignition retards to, first of all, be able to pull it in and out of gear at full throttle, as well as downshifting it without hurting this beautiful sequential gearbox. It starts at the top here with this load cell gear knob. So as I'm applying force or pushing and pulling on the load cell, there's a cable up the top here that applies how much force I'm actually using to shift the gear into the engine management system. I can map then a fuel cut, an ignition retard. So basically how much engine power to cut based on what gear we're in, what road speed we're doing, what throttle position I'm at, what manifold pressure I'm at. So it allows me to release the power while I'm in 4th gear, select 5th gear, reintroduce that power, apply an ignition correction so that it'll feed that power back in slowly in order to engage the teeth of the gears inside the gearbox exactly how we want, and power on. We'll do this hundreds and hundreds and hundreds of times over a race event. So every lap, you countless gear shifting. So this has to be right. We've talked about flat shift up gears. So that means that I'm holding the throttle wide open and I'm ripping through the gears. 1st, 2nd, 3rd, 4th, 5th, 6th. Also we do in this setup is downshift throttle blipping. What that means is that as I'm in 6th gear, belting along, I want to come down through the gears. I'm not going to use the clutch. I'm going to hit the gear knob. It's going to cut the engine power. It's going to blip the dual electronic throttle. So it's going to rev the engine up in between gears. So instead of sort of heel and towing into a corner, I'd brum, brum. The engine management system will do that rev matching for you. So now I'm going to set it up on the dyno so that we're not going to have any load on the dyno. I'm going to be able to rip it up through the gears, blip it down through the gears so you sort of get an idea of what I'm talking about with this sequential gearbox. Then, when we're at the racetrack with the inertia of the car behind it, we'll do the fine tuning of that to make sure that the thing is shifting flawlessly every time. One of the functions that's been so easy to configure now because we're using the keypads, all of the features and functions that require the user to press a button to turn something on, like a latching on off or something like that, straight into a keypad, set it up against a function, job done. It's so much easier now. So for the one that we're going to be talking about is the pit lane speed limiter that this thing needs. I've got a button up here. As soon as I press that, it latches on. The thing now is limited to 50 k's an hour. Press this button again, no more limit. All I'm doing, I'm just using this function here, control type, fixed speed. As soon as I press this button, that means that the speed is going to be locked at 50 kilometers an hour. There's our pit speed limiter. It's that easy. Well, it's made the power. We're going to get it off the dyno, which is always a good way to finish a day on the dyno. I've had a cracking day. I've really enjoyed having the ability to adjust everything and do whatever I want and get the car to drive exactly how I want it. So, with any luck, the next time I see you, we'll be at the racetrack testing this beast. We'll see you next time.